So this talk is on multi-terminal secrecy. And initially, this work was with Imre Csiszar of the Hungarian Academy of Sciences. Much of the work I'm going to talk about today has been published, but Imre and I have been discussing various problems. And then my PhD student, Shagnik Bhattacharya, also got involved in discussions with me. What I'm going to present today is a mix of all our discussions and some conclusions that we have come to, and many conclusions that we are unable to come to. I acknowledge the support of the US National Science Foundation that supported this research. So the outline of the talk, I'm going to present two special models, multi-terminal models for secrecy. One is the multi-terminal source model. The other one is an analogous multi-terminal channel model. And although we are going to talk about secrecy, you will see as we go through the talk that there are intrinsic connections to multi-terminal data compression problems and channel coding problems for transmission without any secrecy constraints. So I'll start with the multi-terminal source model, and there will be three concepts that I'll describe. One is interactive communication, the second is common randomness, and the third one is secret common randomness with an additional constraint that constitutes a secret key. And then we'll get to the multi-terminal channel model. So in the multi-terminal source model, there are M terminals, 1 through M, and the set of terminals denoted by script M. These terminals observe signals that are correlated. And to describe those correlated signals, we have M random variables, X1 through Xm, which we take to be finite valued. And let's say we know the joint probability mass function or distribution function of these random variables. Now, terminal I observes N IID repetitions, xi1 through xin, of the random variable xi, and it will be denoted in shorthand by x sub I sup n. Therefore, terminal I observes an IID data sequence for every terminal I. While the signal at each terminal, or while the observation at each terminal is IID, if I fix a point in time, so let's say I fix a particular instant in time and I look at all the signals across the various terminals, they in general will be correlated, jointly distributed with joint PMS given by this expression. Now, in order to enable additional processing, each terminal also possesses local randomness, which will be denoted by U sub I. And we're going to take these local randomness variables to be mutually independent, and they're also independent of the signals at the M terminals. Now, these terminals, therefore, terminal I is in charge of, say, Yi, which of course depends on N. And Yi is a combination of Ui, the randomness is terminal I, and the signal Xin. And these terminals are going to cooperate to accomplish a given task cooperatively in a distributed manner. And to that end, they engage in multiple rounds of interactive communication among themselves. Interactive communication means, in effect, that the communication from, let's say, time is slotted and terminals transmit in sequence. The communication from any terminal is going to depend on its own, from terminal I, for instance, is going to depend on its own resource Yi and on all the previous communication. We're going to assume ideal conditions. The channel is noiseless, which means that the communication is perfect. Channel is of unlimited capacity, so there are no rate restrictions, and all the terminals here, all the communication instantaneously, which means that communication takes place in an instantaneous broadcast mode. And all of this interactive communication is going to be denoted or depicted collectively by this F, which of course will depend on N. So this is the basic model. Now, this slide simply describes what I described as interactive communication, that the communication from any terminal I in a particular time slot will depend on its own local resource Yi, which is a combination of Xin, the data, and the randomness Ui, and on all previous communication. A special case of this communication with which we are more familiar is simple communication, where each terminal transmits autonomously based only on its own local resource. Now, this interactive communication has a very interesting distinguishing property, which says that if you have random variables y1 through ym, again, remember yi is the combination of ui the randomness at terminal I, and the local signal xin, then if the communication is interactive, so for any interactive communication protocol, the entropy of the communication is bounded below by a weighted linear combination of the conditional entropies of the communication condition on YB complement. So what's the idea here? There are M terminals. We take a cut set B complement, where B is a non-empty strict subset of 1 through M, and then look at its complement. We assign weights lambda B to each of these sets of terminals B. These lambda B's have some properties. They lie between 0 and 1. And if we take any terminal I and sum all the lambda B's for B's in the set, in the subsets of 1 through M that contain the terminal index I, that sums to 1. This lambda is called a fractional partition. It's a beautiful combinatorial object with very many nice properties. And this inequality, equality will hold, for instance, if y1 through ym are mutually independent. So this is a distinguishing property of any interactive communication protocol. For the special case of two terminals, this inequality becomes the entropy of F is bounded below by the sum of the conditional entropies of F conditioned on Y1 and Y2, which is equivalent to saying that the conditional mutual information between Y1 and Y2 conditioned on the interactive communication is less than or equal to the unconditioned mutual information between Y1 and Y2. So this is a distinctive property of interactive communication and plays an important role in converse proofs. Now, we have M terminals that have data. They also have local randomness, and they want to perform a distributed computing task, for instance, but in a cooperative way. And to that end, they communicate among themselves in an interactive fashion, as I just mentioned. Now, what exactly do the terminals do? What they want to do is they have correlated data. They go through these communication exchanges, and they want to convert the correlated data into shared bits on which they agree with probability close to 1. And these shared bits that the terminals will have is known as common randomness. And to make this concept precise, here we go. For any interactive communication protocol F, a random variable L, which is a function of all the random variables in the system, is going to constitute common randomness for these terminals, namely shared bits on which they agree with probability close to 1. If there exist local estimates of L, which I call Li, which is a function of the local resource Yi, which is xin, the signal, and the randomness Ui. Li is a function of Yi and the communication F, the interactive communication. And all these locally generated Li's should agree with L simultaneously with probability close to 1. So these shared bits are described in this way. And such common randomness can be used by the terminals to perform a cooperative distributed processing task locally. And the communication allows them to build shared bits, which they can use in performing this distributed processing task, but locally. So a natural question that arises is, what is the maximum amount of such common randomness M terminals can generate using a given communication protocol? This maximum amount of common randomness is measured in terms of maximal common randomness rate, and it is the conditional entropy of L given F. Because the terminals communicate and everybody hears all the communication itself is known to everybody and therefore constitutes common randomness. But what we are seeking is the common randomness that the terminals can generate, namely L, that is distinct from the communication that was used to generate it. And that is measured by the conditional entropy of L given F, because this conditioning serves to purge the common randomness L of the communication that was used to generate it. And we look at the rate of this common randomness. And the question is, for a given communication protocol, what is the maximum common randomness rate that can be generated by these M terminals? So I want to stop here and pause here and ask, is the model clear? Hello?
Yes, so we ask if the model is clear. So is there anyone who would like to ask a question at that point? So it seems the model is clear.
Very good. Thank you. So this is a basic operational question, and this question and the answer to it is useful in analyzing distributed processing tasks that use interactive communication. So what is the answer to this question? Namely, what is the maximal common randomness rate as measured by this limit of the conditional entropy rate of the common randomness L condition on the interactive communication F that can be generated by any given interactive communication protocol? And the answer is this, given by theorem one. So for any common randomness achievable with any interactive communication, for every n, the common randomness rate is bounded above by the entropy of all the random variables in the model, the x random variables, not the random variables u1 through un, the main random variables x1 through xn, minus this quantity that we saw in the distinguishing property of interactive communication maximized over all fractional partitions. And this quantity is a fundamental upper bound on the conditional entropy rate of any common randomness achievable with any interactive communication, normalized, of course, here by n. And this is true for every n. And so the proof of this fact relies on the distinguishing property of the interactive communication that we saw a couple of slides ago. And therefore, we see that for any common randomness L in this model achievable with interactive communication F, the conditional entropy rate for any n or every n is bounded above by this quantity. And in fact, this upper bound can be attained. In fact, it can be attained not necessarily by interactive communication, but by using simple communication. And as the common randomness rate, which is equal to the normalized entropy of all the random variables, x1 through xm, with the ID repetitions. Now, this constitutes omniscience. So in effect, what's going on here among the terminals is that they have local data, they have local randomness, they communicate interactively, and through this interactive communication, they become omniscient, which means that each terminal learns all the signals of all the other terminals. So that is this conditional entropy, this entropy rate, minus the minimum amount of communication, the sum rate of communication that was used, namely the rate of f that was used to attain this omniscience. So the difference between the total randomness rate, which corresponds to omniscience, and this quantity is exactly equal to the joint entropy of x1 through xm, because the data at each terminal are IID, minus the minimum sum rate of communication that is needed by all the terminals to attain this omniscience. And in fact, this concept has also been considered recently in the quantum literature, in the work of Farmin Salek and Andreas Winter, where there are multiple parties with quantum correlations, and these quantum correlations are converted into classical and quantum common randomness using LOCC, namely local operations and classical communication. So with this as the basis, namely the formation of common randomness using interactive communication, we come to the notion of a secret key, which in effect is secret common randomness, namely it's common randomness that has to meet an additional secrecy constraint. So now the interpretation is that the public communication that was done, what was exchanged by the end terminals, is observed by an eavesdropper. And now the terminals wish to generate common randomness L that is independent or nearly independent of the communication that was used to generate it. And so the public communication F is observed by an eavesdropper. Now the terminals 1 through n generate common randomness L that must satisfy a secrecy condition. So we want the common randomness L to be a secret key, so it should satisfy two constraints. It should be nearly uniformly distributed, and it should be independent of the communication that was used to generate it. So the Kullback-Leibler divergence, this is a secrecy condition. The Kullback-Leibler divergence between the joint distribution of the common randomness and the communication on the one hand, and the uniform distribution on the common randomness space or the key space and the communication should be close to zero. if we evaluate this divergence, a simple calculation shows that this is a log of the cardinality of the common randomness space minus the conditional entropy of L given F. So for this to be close to zero, L should be nearly uniformly distributed, and also it should be nearly independent of the communication F. So this is a secret key. In particular, we see that the conditional entropy rate of the common randomness given the communication is in fact equal to the entropy rate of the common randomness L. Yes. So now the question becomes, what is the secret key capacity of a multi-terminal source model? In other words, what is the largest rate of a secret key that can be generated by these M terminals in this multi-terminal source model? uh, that is independent, that is nearly uniformly distributed or uniformly distributed and independent of the interactive communication that was used to generate it. And that secret key capacity is equal to the joint entropy of all the random variables x1 through xm in the system, other than the randomization variables u1 through um that were mutually independent of themselves and everything else, minus this quantity here, which is the linear combination of the conditional entropies. And this is attained as a secret common randomness rate for large values of n using just simple communication from the m terminals. And this, by the previous result, this entropy rate of the common randomness or the key is equal to the entropy rate that corresponds to omniscience minus the minimum sum rate of communication that was needed to obtain omniscience. So we see that the secret key generation problem, the optimum secret key rate generation problem, is inherently linked to a purely data compression problem without any secrecy constraints, where the M terminals with local data wish to become omniscient. For instance, each of the terminals has portions of a large file, let's say, and each terminal wishes to form the entire, to learn the entire file. And to this end, they all exchange communication among themselves until they become omniscients. So omniscience and secret key generation are really strange bedfellows. If you look at the case of just two terminals, x1 with x1 and x2, then this quantity on this right, the secret key capacity, is just the mutual information between x1 and x2. It can be shown that can be shown by a simple calculation. And of course, the mutual information between x1 and x2 is the Kullback-Leibler divergence between the joint distribution of x1 and x2 and the product of the marginals. So a natural question that arises is, can this expression here be written as a divergence? Because that would make for a useful representation of this quantity here. The answer is yes. And the expression is, the concept is called shared information. In other words, this right-hand side here, this quantity here, can be written as a Kullback-Leibler divergence. And it has a name called shared information, because shared information, you recall that when I said that when you have two terminals, then this expression is equal to the mutual information between x1 and x2. So this is for two random variables, x1 and x2. A natural question is that if you have m random variables, what is the counterpart? It's called shared information. Shared information, as it turns out, is a potential measure of mutual dependence among an arbitrary number of discrete random variables. And so the previous secret key capacity can also be expressed as the shared information of the random variables x1 through xm, which has the following description. So the idea is given by this picture. You have m random variables x1 through xm. Let's take a partition of the number of the terminals 1 through m, and these are the atoms of the partition. In each of the atoms of the partition, all the random variables that fall in an atom are clustered together, they're coalesced together. So we look at the joint, the divergence between, so in other words, in this picture, there are, let's say, this 1 through m, the terminals, are partitioned into k atoms. Then we look at the divergence between the joint distribution of x1 through xm and the product of the team marginals when each team or each atom, all the random variables are clustered. Divide by the number of teams, which is k here, minus 1, and minimize over all non-trivial partitions of 1 through m. In other words, for a given k, look at all possible partitions of size k with k atoms, and then minimize over all sizes of partitions ranging from 2 atoms to m atoms. And in fact, Chung Chan and his collaborators have done a very comprehensive and consequential study of shared information. They call it multivariate mutual information. And as I said before, the shared information is a potential measure of mutual dependence among an arbitrary number of discrete random variables. And there's a rich body of literature that deals with shared information in various contexts. So this is multi-terminal secret key generation and its connection to multi-terminal data compression without any secrecy constraints. Next, we get to the multi-terminal channel model, which is the following, which is shown by this picture. We have a discrete memoryless channel. There are M terminals that are using this channel. They all cooperate to generate secret key. So they cooperate in secrecy generation. Terminals 1 through K govern the inputs of a secure discrete memoryless channel. All the communication through the channel is secure. And the terminals K plus 1 through this should be M, sorry, K plus 1 through M observe the corresponding outputs. So K terminals, K can be anything from 1 through M minus 1. So K terminals control the inputs of the secure DMC, and K plus 1 through M observe the corresponding outputs. This is a discrete memoryless channel, and so the terminals send data through the channel. And between the input terminal I, for instance, which lies in 1 through K, transmits the sequence XIN, XI1 through XIN. These need not be IID over the channel, and any output terminal I observes a corresponding sequence of length n. Now, between these simultaneous secure transmissions through the channel, all the terminals are allowed to engage in interactive communication over a public channel as before. So before every transmission over the channel, the terminals can engage in free public communication, and this public communication can determine the next channel input from the various terminals. And again, all of this public communication is going to be denoted by F, which of course is a function of n. Local randomization is also available at the terminals. These are mutually independent random variables, U1 through UM. So now the question is, what is the secret key capacity that can be generated by the M terminals? So the resources that they have at their disposal are twofold. One is secure communication through the channel, and the second one is between every transmission through the channel, simultaneous transmission by the K input terminals and corresponding reception by the output terminals. All these M terminals can communicate freely over a public channel, but this public communication is observed by an eavesdropper, but not the communication through the channel. So there is no wiretapping. Well, one obvious solution is what is known as simple source emulation. The input terminals 1 through K can transmit over the channel n IID repetitions of the random variables x1 through xk, one corresponding to each of the input terminals, such that they are independent. There's a more general form of source emulation, and the more general form of source emulation is where the input terminals generate some correlation among themselves. So the idea here, the source simulation, is that the input terminals send data in this IID fashion for source simulation over the channel. The output terminals observe the data, and then that puts us back in the framework of a source model that we saw earlier, and we can look at the secret key capacity of the source model that we saw earlier. Now, in order to, the simple source emulation has the drawback that the input terminals don't have any correlation among themselves. They are independent. So in order to induce a correlation among the input signals, we have general source simulation. To that end, let V be an auxiliary random variable, which also takes values in a finite set with the property that the output of the channel conditioned on the inputs is conditionally independent of this random variable V. So there's a Markov chain. And for every V, the input terminals send data that are conditionally independent. So the way this is actually implemented is that one input terminal generates and reveals n IID repetitions of the random variable V through public communication. And then the input terminals 1 through K transmit over this channel, which transmit n independent versions of these conditional independent random variables in this way. So some correlation has been induced between the channel inputs. And V is free, so the input terminals can choose V in any manner they want. So clearly, a general lower bound for secret key capacity for this multi-terminal channel model through source emulation is the following. Through general source emulation, it's always bounded below by the secret key capacity of the general source emulation model, the way I described it. But then the input terminals have choice of V, the joint distribution of V, and the input random variables x1 through xk, such that x1 through xk condition on V are conditionally independent. Now, we know a single letter expression for this secret key capacity. It's just like the expression we had before, except that V, there's additional conditioning on V. Now, the input, one of the input terminals generates this random variable V, n ID repetitions of it, and then broadcasts this publicly. So the eavesdropper has access to the V sequence. So when a secret key is formed, it must be independent of this V sequence and also of the public communication that was used by the M terminals in between channel transmissions. And this expression is, in fact, can be written in terms of a shared information as before, except that it's a conditional shared information. So there is a concept of conditional shared information, which is the same as the shared information that we saw earlier, with the exception that there is additional conditioning on the random variable V. This right-hand side is achievable. So this is a lower bound on secret key capacity for the multi-terminal channel model. And it can be shown that this right side is achievable by a simple communication protocol, namely with the input terminals not sending any public messages at all, except for the initial transmission of the V sequence, and with each output terminal sending at most one public message based only on its observed output sequence. So it can be shown that general source emulation can yield larger secret key rates than simple source emulation. For the case of a multi-terminal channel model with one input terminal and m-1 output terminals resembling the broadcast channel, because there's only one input terminal, there's no need to build correlation among the input terminals. There's only one of them. And it turns out that simple source simulation suffices to attain secret key capacity. And so a natural question that arises is when you have multiple input terminals, does general source emulation attain secret key capacity? And this is an open question. Now, there are many interesting consequences of multi-terminal channel models. As I said, there are nice connections to transmission problems, channel transmission problems without any secrecy constraints. So one of these models, one of these settings is the well-known multiple access channel like model where you have m input terminals and one output terminal. So terminals 1 through m-1 control the inputs of the DMC, and terminal m listens to the output. Now, of course, we know the average error capacity region for this discrete memoryless multiple access channel. This is a well-known quantity. Now, what is this connection? What is the connection of secret key capacity to the transmission capacity region of the discrete memoryless channel? The question in general remains open, but there are some consequences. There are some observations. The secret key capacity is positive if and only if we have rates R1 through Rm-1 corresponding to the m-1 input terminals in the capacity region such that each of these Ris is positive for each of the Is. In other words, the secret key capacity for this model is positive if and only if the transmission capacity region, the average error capacity region of this discrete memoryless multiple access channel has a non-empty interior. Now, the second observation is that we know the capacity region, the channel transmission average error capacity region for this channel. And look at the boundary of the capacity region at the equal rate point, where all these senders send at the same rate R, and look at the maximum such rate on the boundary of the capacity region. Then the secret key capacity is always bounded below by the maximum equal rate point on the capacity region, namely the transmission capacity region, without any secrecy constraints of the underlying discrete memoryless channel. And any R can be attained with RRRR being with R any secret key rate any R with R through R being a point on the boundary of the capacity region can be attained as a secret key rate with no public communication by the input terminals and with only with only the output terminal sending sending a public message. Furthermore, R is an achievable secret key rate by general source simulation only if it corresponds to the maximum equal rate point in the capacity region. So these are some of the connections between the best the secret keys that can be attained for this multi-terminal channel model and the capacity region of this multiple access channel, which is known. Uh, I want to conclude with one example. This is the famous natural question that arises in this context is that uh, the feedback capacity region of the multiple access channel is not fully known except in special cases. And one of the cases for which it is known is the famous arithmetic adder channel, where you have two inputs and one output, and the output is the arithmetic addition of the two inputs. So the channel is described with has input 0 and 1 for each of the terminals, and the output is 0, 1, 2. And the output is the arithmetic sum of the two inputs. There's no extraneous noise. We know the capacity region of this channel is given by this expression. And so the rate pair 0.75, lies on the boundary of the capacity region. And therefore, by the previous theorem, a secret key rate of 0.75 is attainable for all the terminals 1, 2, and 3. This can also be attained by simple source emulation. A natural question to ask is what can you say about the best secret key rate when there is public communication in the form of receiver feedback to the two transmitters? Now, the feedback capacity region of this specific channel is known. It was looked at by Tom Cover and Cyril Leung, and then by Franz Willems. And we know that the equal rate point in the feedback capacity region is 0.79113. And it can be shown now, of course, when you send feedback, some of it is the feedback, of course, is over a public channel, and so the eavesdropper gets to see it. So not all of the feedback can be used to obtain gains in secret key rate. What can be shown is that for this specific channel model, the secret key capacity cannot exceed the maximum equal rate point in the transmission capacity region of this this arithmetic adder channel with feedback. Is this result true in general? Not known. And even for this very simple channel model, secret key capacity is not known. So, in closing, there are many basic open problems that remain open for this multi-terminal channel model. When we look at proofs for achievability, what we don't understand fully now are the precise trade-offs between the gains that can be obtained in channel transmission rates over these multi-terminal channel models for transmission using coding schemes that are bolstered by interactive communication among the terminals between channel transmissions on the one hand, and information leaked by this public communication to the eavesdropper. That is in the realm of achievability proofs. For converse proofs, unlike in the case of the multi-terminal source model that we saw earlier, there are no general computable single letter upper bounds for the conditional entropy rate of the common randomness that is formed by the terminals, which when conditioned on the public communication will lead to a secret key rate. And indeed, even coming to so brand new ideas are needed. I think at this point, it is fair to say that to make inroads in terms of making inroads in answering these questions, we really need some brand new ideas. And since this is a workshop, I thought I would throw open these problems so that people can, if they are interested, can consider them. And in fact, even for the multi-terminal source model, which we saw earlier, there are many open problems. We assumed that the public communication was observed by the eavesdropper, but the eavesdropper also could have access to side information, wiretapped side information in the form of sequence ZN, which has a joint distribution with the signals observed by the given terminals. Except again, in special cases, we don't have a single letter characterization of this wiretap secret key capacity, even for the case of two legitimate terminals. There are upper and lower bounds. There's been a rich body of work, but a full answer is not yet available. And also, when we have these multi-terminal models, different groups of users could want secret keys for themselves, for the groups, which are concealed from the other groups. So what happens to the formation of group-wise secret keys? Answers are known in special cases, but the general problem remains open. And with that, I thank you.
Yeah, thank you very much for this very interesting talk and also the many open questions that are very encouraging for the young and early stage researchers to go in this direction. So we have still time for some questions.
Thank you very much for the very interesting talk. I'm Anton Trushichkin from the Düsseldorf University. In the very first talk, I applied theorems you told about multi-terminal source models to quantum networks.
Yeah.
I have the following the question about the shared information. As far as I understand, in this talk, you consider the case of no helpers. So all participants are secrecy seeking.
Yes.
And in this case, yes, lambdas has a structure relatively simple, but in the case of helpers, it does not is not reduced to this expression with.
Yes, you're right. So there are two things to be considered. One is, let me see if I can go to a picture and address your question. So coming back to this first question, let's say terminals 1 and 2 alone wish to generate a secret key with help from the other terminals, right? And in that case, too, the secret key capacity is known. It is in terms of an expression that looks like this, but it doesn't lend itself to a formula that looks like shared information. So yes, that shared information formula has an analog, a counterpart, that turns out to be an upper bound for secret key capacity, but it need not be tight. So there are counterexamples where it is not tight. Now, if on the other hand, the other terminals, they are helper terminals, uh, they try to help, and we want secrecy from those helper terminals, which means that those terminals can reveal their data to the legitimate terminals. Then the bound is tight. So in other words, you can show that this notion of conditional shared information is a tight upper bound for what is known as private key capacity. But when you have just terminals that are helpers, and the key that is formed has to be independent only of the eavesdropper's observations of the public communication, but the key need not be concealed from the data seen by the other by the helpers, then yes, you're right that the upper bound that we get, there is an upper bound in terms of shared information, but it need not be tight.
Yes, and my question is whether do we know something about this quantity with arbitrary lambda, arbitrary fractional lambda, so the quantity appearing in this scenario with helpers? Can something be said?
That I do not know. I don't think there is a general answer. So you're saying instead of taking the maximum over the fractional partition, you fix some arbitrary lambda and look at the quantity that you get, which of course will be an upper bound. Can we look at it as a function of lambda and say when you get maybe the best possible upper bound through this variation? I don't know the answer to that question. No.
Because yes, in my problem, I told that in your case, this shared information is reduced to bipartite sum of bipartite mutual information, but with arbitrary fractional partition don't, and it's a problem for some quantum to do some quantum stuff. So yes,
I see. So please do write to me, and I will be happy to discuss this matter further with you. Yes. So for us, the upper bound, when you have just helpers from whom you don't need additional secrecy, the lack of a tight upper bound. Of course, the capacity formula is known. So there is a formula like this where the lambdas have to satisfy some additional constraints. So we know that the secret key capacity with helpers, but of course we don't have a formula which looks like this one here. That is the drawback.
Yes. Okay. Thank you.
On the other hand, so I should add that there is a conditional version of this, which is called conditional shared information, that becomes a tight upper bound when these helpers there's a requirement in the problem that the key must be concealed also from the helper's observations, in which case the helpers might as well just release the information to all the legitimate terminals, and the resulting key must be concealed from the eavesdropper's observations of the public communication, and also this data that was revealed by the helpers. This is called a private key capacity. And there is a bound of this kind, upper bound, which is tight, except that this becomes a conditional divergence.
Okay, thank you very much.
Thank you.